Okay, this is a little video about parallax. Now, using GeoGebra to basically make the points that need to be made. So we're going to start first with something which is not parallax, but sort of forms the basic foundations for it. Essentially the picture is we want to measure some distance, basically the distance between C and D, for example. This could be the height of a tree, for example. And we have two ground-based measurements. One which is over here at point A, and one which is over here at point B. Now, one way of doing this measurement is to kind of have it be symmetrical. Makes it a little easier, but I want to prove a point about it being not symmetrical, so we're just going to go with this for now. All right, anyway, so the first kind of fact that we have is what the distance is between A and B. Excellent. And so, and what we kind of want to know is the distance between C and D. All right, obviously, GeoGebra tells us it's, let me call that CD, so that's clear. Delete. All right, I'll just call that CD. Distance CD, and just to make it all clear, because we'll need these to make some points, distance from A to C, and the distance from B to C. Now, the only number that we can directly measure in our setup is the distance from A to B. And also maybe from A to D if we know where D is. But maybe we don't know where D is. So maybe we just do A and B and we get this. All right, so we got that distance A to B. The next thing up is the angles. So angle CA, angle D, let me just say, angle BAC, it'd be the same as the angle from what? Oh, oops. Angle BAC, there we go, 45 degrees, and the angle from CB to A. So those are our two base angles of what would be a triangle ABC. And if you have the two angles and the side length between those angles all known, then you've defined the triangle. And you can kind of see that being true here, because look at A. We've kind of got this angle that we've shown. That line segment gives us that direction. So we can just kind of extend it through. It's going to line up on C. And then you've got one from B going through here, and C is where the cross point is, the intersection, right? And so that defines a triangle. There is no kind of any question about it, so yeah, we're kind of done. Now, mathematically, the way we do this, we figure all this out, is essentially the height CD of the triangle ABC can be found by considering the right triangle CDA and CDB and getting the tangent of alpha here, this angle. So there's a function called tangent. There's an angle alpha that you plug into the tangent function. It gives you the ratio of this height here, CD, to the height AD, or into the length AD. And then it also gives you the tangent of beta, gives you the height CD again, and the length dB. Now we don't know where D is, so we don't know what the lengths AD and DB are. But if you kind of play around with the algebra a little bit, you can find out that the formula would be the distance AB divided by 1 over the tangent of alpha, and then plus 1 over the tangent of beta. Okay, just some sort of math gobbledygook. Don't need to worry if that's, gobbledygook. That's fine. Doesn't matter. The point is, with the two angles and the side length AB, you can compute the height. And heck, you could just draw the triangle in GeoGebra and get that. You can scale these things. It's fine. Triangles scale just fine. Whatever. It's known. Moving on. Okay, so and you see here that the height was indeed 1 from this little formula. And now as we move point C, everything kind of scales. Notice, of course, that the length AB is not changing as I move this point C and getting farther and farther away. But what's happening to the angles alpha and beta? Well, they're getting sharper. They're going to right angles. Basically, that's kind of the limit. And notice that the lengths AC and BC, they're different. If I were to move B over to here to 1, then they'd be the same. The angles are the same and all that good stuff. But with them being different, you get the different sizes. But they're getting closer and closer, and in particular getting closer to CD. And that just continues on. All right, good. Now, so that's kind of terrestrial angle measurement, right? If you can measure the angles alpha and beta and the distance between these 2 points AB, you could figure this stuff out. Now, when thinking about Mars, trying to find out how far away Mars is, you could take 2 points on the Earth's surface that are far apart, say New York and LA, and their distance is about 2,500 miles, and you measure where Mars is. If you can compute the angles alpha and beta, accurately and so forth, that would be good. But, here's a problem. So Mars is about, let's say, 50 million miles. It varies based on how close. The closest approach was, I think, 33 million. And I guess when it's farther, the farthest is something like 200 some million. Distance from the Earth to the Sun is 190 million. So, goes on the other side. And, well, I guess it's probably more than that then. Anyway, it doesn't matter. It's a lot of distance. Let's go to, so 2,500 and say 50 million. That's about 20,000 difference. Let's just start with going with C to, say, 100. Let's see, can I? Yeah. So here's showing all the objects. Ooh, that's not the axis scale that I want. Oh. Okay, I guess I just need to scroll this way. All right, so scrolling out, look what happens. So the points A, D, and B are all lining up. This is only 100 times this far, right? I said 20,000. Look at the angles alpha and beta. They're practically right angles. 88.8 and 89.4. Look at the distances here. Distances AC and AB are almost 100, which is almost the same as CD, which is 100. And H is starting to get a little weird and whatever. That's just GeoGebra being a little bit crazy. I don't really know why. Oh, I guess just jiggle it a little and it's fine. All right. And then let's see what happens at 1,000. Whoa, even more so. Very similar to an isosceles triangle, right? AC, BC are almost the same length at this point. because it's so narrow, even though AB hasn't changed at all. Those angles, they've become almost the same. And at 20,000, okay, you see that they're 89.99, both of them, and so it's like the 5th decimal digit over is when they start to be different. And this is kind of the scale we're talking about, right? They're essentially 1 dot, and there's this C. Okay, good. So these angles, alpha, beta, are kind of hard to measure. So let's go back to the more zoomed in view, standard view. Here we go. And what do we have here? Well, we got these two angles. What if we were to form the angle at C? So let's see. So here, when C is really close, it's a pretty big angle. These two angles, alpha and beta, they're different, and so knowing just the angle here at C is not enough. Angle and a side apart is not enough. It would be if we had an isosceles triangle, because, well, isn't that nice? It's actually a right triangle, but whatever. Just to mess that up a little, the isosceles triangle means angles alpha and beta are the same, which means that if you knew the angle gamma and that this triangle was isosceles, you could get the other two angles by subtracting this angle gamma at C from 180 and dividing into 2. Excellent. Now let's just move B back. So it's not an isosceles triangle, but whatever. Now let's go back to being far away. Okay, and what do we have? Well, so now these angles are nearly the same, and so angle gamma could be considered, you subtract this angle from 180 and divide it into 2, and those are approximate, presumably be the midpoint between angles alpha and beta or something. I don't know, probably doesn't quite work, close enough. Anyway, so there's a certain sense at which knowing the angle at C could tell us what we want, and maybe we just need to go back to the standard view. Oh, where's my C? Okay, zoom in here. Now, basically, again, it's sort of like trying to view triangles ADC and BDC as right triangles. And if you know the angle at gamma, or half the angle, I guess, gamma, and if it was actually isosceles, let me find where one appears. Okay, so now it's isosceles. Then half of this angle is going to be in the right triangle ADC, and the other half CDB. And so we can use tangent again, our little friend. Tangent of this angle gamma, or half the tangent of gamma divided by 2 is equal to, I'm just kind of writing the input what I'm trying to say here, is equal to AD divided by CD. Okay, don't hit enter if you're following along, because I'm not computing anything here. I'm stating that this would be the fact. So it's the opposite side from the angle gamma, AD, divided by the adjacent side, CD, and that's what tangent means, right? So what did we care about? We cared about CD. So if you take CD, let me just call that H2. Or maybe capital H. I'll call it capital H. Yeah, that's a nice one. And let's see, so what did we know? We knew, what was it? So CD is what we cared about. We put that on the other side. And so I guess it's tangent down here. Gamma over 2. And we'll just do AD over 2. And that would be, oops, not AD, AB. Because we're saying that that's kind of, so the idea is the isosceles triangle D, point directly below C, divides AB directly in half. So AV over 2 is AD, and tangent of this angle gamma in half again would be the angle ACD. And if I'm right, there we go. Look, that's nice. Isn't that nice? Now, okay, that's good. And of course, if I drag this point B, that's no longer true, right? H is 4.05 now, instead of just 4, as it should be, because it's no longer isosceles. But whatever. Let's now try to scale that out. I wonder why it's going slowly now. All right, C. Let's try going back out. Wow. Okay. There is C up there. You can still see kind of this, the distinct points here, but it's getting kind of close to the right angle. And look at H, this height that we're doing. We're assuming it's an isosceles triangle when we know it's not, but it's almost is. And, you know, 100.00, right? It's already pretty decent. Okay, great. Now, we're back in here. So that's great. So I've kind of demonstrated that if you knew the angle gamma, particularly for the far away stuff that we're thinking about, you could get that distance. Okay, one problem is, of course, like let's say we're measuring where Mars, how far Mars is, right? Well, we're not at Mars. We can't measure the angle between those 2 points. You'd think you'd even have a better chance of measuring the angles at A and B than you would at angle C. This is where parallax comes in. So to witness parallax in action, take a moment and put your thumb out in front of your face, far away. Extend your arm all the way. Look at your thumb. Close one eye. Notice where your thumb lines up in the background. Now close the eye that was open and open the other eye. Now look at the background and where your thumb is. Did you see it shift? So your thumb didn't move at all, of course. It's just the perspective of having these two different viewpoints. If you have, you know, both eyes open, particularly after doing this exercise, your brain is sort of like, what? But anyway, the idea is that because the background doesn't really seem to move very much, but the thumb does, what we get are these sight lines. So let's draw in these two lines, BC and AC. So these are the sight lines. You can see past C, let's think of that as Mars. You see what stars in the far distant Mars would line up when viewed from A and when viewed from B. Okay, and now we put put some point on here, on F, and just to make my life a little bit easier, I will draw on a perpendicular to the y-axis, hitting the other line. Just a little bit of a setup here. Okie dokie, and get rid of that line. It's distracting. Now if I move E, F will move along with it. Great. Okay, so what you say? Well, I claim you can figure out the angle gamma approximately with this information. So how do you do that? Well, I'm just going to put in a new point. So this could be A or could be B. It could be some third point also on the surface of the Earth or something. Whatever. Doesn't matter. Just so long as it's basically really close to AB relative to the very distant stuff, E and F. Those are distant stars. And when we say distant, we mean distant, right? We're talking, so if you're on the surface of the Earth trying to do this with Mars, you're talking 2,500 mile maybe separation on Earth, 50 million miles to Mars, and, you know, maybe 100 trillion miles to the stars that you're measuring in the background, or even further. You know, if you're measuring to a galaxy in the back, it could be 1,000,000 light years. Whatever. Far away. Okay, good. Now, let's get that angle going there. So angle angle FGE. There we go. All right, why do I care about that angle? 4.46 degrees. That doesn't seem to correspond to gamma or anything. That's terrible, James. That's terrible. Well, okay, let's scale this guy out. Well, what happens as I move the distance part? Remember, this is thousands of times distant from where C is. Oh, look at what that angle delta is doing. It's getting closer and closer to 17. We're now 300 places away from where the other points are, and now 16.5. And this is nowhere near as far as it actually goes. It's thousands of times. And remember also that C, I had C pretty close to these points. And it's close compared to like where E and F are, but it's nowhere near the stuff. Notice as I move C farther away, all of a sudden everything's getting more narrow, right? And so that angle delta, all of a sudden 1.7 degree 70 here, and gamma is 1.71 there, right? So, and then if I move it all the way out there, that angle is now 0.17, 0.17. Okay, and as I scroll out, where the heck did the C and the E go? I don't know, man. They went far away. There we go. They're way out there. And if I bring this stuff back in closer, the angle gets less. But again, these are far away points. And so, that's the prescription for measuring the parallax. You pick your 2 points that are kind of close relative to all that far away stuff. You figure out the distance from that. And then you do your line of sight to the distant stars of your near object where it lines up with those distant stars. And then you measure the angle between those two distant things. And it doesn't matter where you are nearby that does that. And it will give you this angle at the top, and you assume it's an isosceles triangle because it approximately is, and you're good to go. That's parallax. Now this is also used, so I mentioned Mars and having 2 points on Earth that are measuring it and seeing where Mars lines up in the night sky with other distant stars. You can also do that with our closest stellar neighbors, but not from Earth, 2 points on Earth. Instead, what one does is use Earth's orbit to get a larger distance. So the basic idea is the points A and B that I had would be Earth at say 6 months later from where it is. So you look at Earth, say in January, looking at this nearby star and seeing where it lines up with the distant stars, and then you wait 6 months and you do it again, and then you can measure the distance between those distant stars. Now, because this is now a measurement that's spread through time, you do have to consider possible actual motions instead of just this parallax motion. When you're measuring, say, on Earth at 2 different points and Mars, you do it at the same time, then you don't have to worry that something else is moving. That motion is pure parallax motion, namely just where you're observing from is changing. But now if you're doing it in time, you have to account for the fact that things might actually be changing. So it's a little bit more complicated than that in terms of, ensuring that you're not sighting up with something else that's actually moved in some other way. However, these distant things don't move a lot relative to us, so, apparently. So it's not that big a deal. So anyway, that's parallax. The idea is by shifting your own position, you can measure the distance of something far away just by knowing that kind of angle change in the line of sight. Again, this is mostly for something very far away. To give you a sense of scale, for the nearby neighbor star, they use the distance between the sun and the Earth, which is about about 100 million miles. And then our nearest neighbor, I think, something like 20 trillion miles. I don't know. And then, the distant stars is like many times that factor. And so things are very, very large. This is also where they come up with the term Parsec. I think mostly people use light years a lot more now because that's a little easier to understand. But Parsec came from parallax arc second, because the measurement of the differences was like in arc seconds. Here we have it in degrees. An arc minute is 1/60th of a degree, and an arc second is 1/60th of an arc minute. And so it's a very, very tiny difference. And so using that solar kind of parallax motion of the Earth on one side of the sun and then on the other, a parsec is 1 arc second of this parallax angle measurement, how far that actual distance is. I think it's about 3 light years. Anyway, that's parallax for you. And the main takeaway is simply you draw some triangles, as we did, and you make some assumptions that are false, but they're approximately true for the kinds of scales that we're looking at, and you just don't worry about it. So that's parallax. Thank you.